Hi guys, welcome back to my channel. In this video, I'm going to show you the full solution of 2022 Paper 2 Higher Level of Time Zone 1. No bullshit, let's go. Question 1. You got a complicated setup. There is a box and a load. They are moving on a ramp. According to the question, the pulley is frictionless. But the friction between the base of the box and the ramp therefore here is non-negligible. Then in question part A, we're going to tell two differences between the momentum of the box and the momentum of the load. Momentum is a vector quantity, which means we shall consider its direction and its magnitude. The direction of their momentum depends on their direction of motion. The box is climbing up, but the load is falling down. Therefore, their directions are different, which makes the direction of momentum being different. Moreover, they're connected through a string. This string ensures that they are moving together at the same speed. But they have different masses. According to the equation of P equals to mv, they share the same speed but different mass gives a different magnitude of momentum. Therefore, the final answer is the direction of motion is different. Also, the magnitude of momentum is different even though their speed are the same. Part B, we are given with the acceleration of the load going downwards by 2.4 meter per second square. With this given information, we are going to get the tension in the string. Let's take a look at the free body diagram of the load. There is a weight. The weight is given by its m times g, therefore it is 3.5 times 9.81. And the upward force is the tension. And be careful, while you draw these upward tension, make sure the arrow is shorter than the downward weight, such that you can get a downward net force and the load would accelerate downward. The tension is the question mark here. So we can get the net force on the load is the downward weight minus the tension. And the net force according to the Newton's second law is equal to m times a. The downward weight is 3.5 times 9.81 minus the unknown tension. Mass is 3.5 and the a is given 2.4. After rearranging, you will get 26 Newton. Next, part C. Our target is to show that the speed of the load when it hits the floor is about 2.1 meter per second. Note that it is a show that about question. Therefore, our answer should be in 3 sig fig or even more. How do we calculate the speed of the load? We can take a look at the Sulfat equation. The reason is, it is a uniformly accelerated motion, therefore all Sulfat equations they are available here. And let's determine which Sulfat we take by constructing a Sulfat table. SUVAT on the left column. On the right hand side, we fill in all the missing information with the premise of downward being positive. It's not a must, but right now the load is falling down, so it's better to take downward being the positive direction. The displacement it moves is 0.95 meter. The initial velocity was 0 because it was released from rest. The V is definitely our target here. A is going downward, but it is not 9.81 because there is a tension going up. The acceleration downward, however, is the given information 2.4 meter per second square. And just screw the time, we don't need it. Just pick an equation without t, which is v squared equals to u squared plus 2as. V squared is the unknown, u is 0, a is 2.4 downward, therefore positive, and the displacement is 0.95 positive as well. After putting these into your calculator, and you will find v is 2.14 meter per second. After the load hits the floor, the box keep on traveling for a further 0.35 meter along the ramp, and after that it will come to rest. Let's determine the average frictional force acting on the box along the ramp. And the forces acting on the box are as follow. Firstly, there is a weight and there is a normal reaction going perpendicular to the surface, and don't forget the frictional force going down the ramp. And next, let's consider the energy conservation as it travels up. The work done on the box is actually the energy transfer, and which is the initial KE it had. The initial KE it had, it is the half mv square, and it is equal to the net force times the displacement it has traveled. The net force is the unknown here, and the displacement it has traveled up is, according to the question, 0.35 meter. The mass of the box is given 1.5 kg. The speed of it was 2.1 meter per second. So the net force, it is 9.45 Newton. However, this is not the final answer because the net force consists of two parts. Part of it is the frictional force, therefore our target, and also a component of the weight. It is the sine theta component. Next, we have 9.45 equals to our unknown plus the weight, which is 1.5 times 9.81 times sine 30 degree. The frictional force is 2.1 Newton. In part E, we have a horizontal table, and on top of it there is a box. The box and the table, they are rough, and there is a friction between them. It could be a static friction, it could be a dynamic friction. It depends on the motion. And it's always true that between two given surfaces, the static friction is greater than the dynamic friction. So that we can take a look at the following force diagram. On this table, there is a stationary box, a tension going to the left, and there is a friction going to the right to oppose the motion. And this force is a static friction because it's stationary. However, the tension force is greater than the static force, which makes a net force going to the left. Next, now the box is in motion. It's moving to the left under the same tension as the previous one, but right now the dynamic friction should be even weaker. The reason is, just like above, the coefficient of static friction is always greater than that of dynamic, which makes the dynamic friction weaker. So that the net force here is even more obviously heading to the left, and the object must be accelerating. You can give your answer as follows. The coefficient of static friction is greater than that of coefficient of dynamic friction. You can write it in English as well as in symbols. The next part is the force. The force of dynamic friction will therefore be weaker than that of static friction. And lastly is the net force. There will be a net force heading in the direction of tension, and such net force will give you an acceleration. This is a conclusion based on Newton's second law. Question 2, thermophysics. Cold milk is going into the heating elements, and then it will become warm milk coming out. The temperature, it was 11 degrees Celsius, and then it is 84 degrees Celsius. There will be 55 grams of milk going into the sterilizing unit in every second. The specific heat capacity is given here. Our target is to get the power input to the heating elements. Power is defined as the energy transfer over time. In this case, it is the thermal energy transfer over time, which is mc delta T over time. Let's rearrange it to make it m over t in one single fraction followed by cm delta t. The reason is m over t is actually 55 gram per second. This is m over t. Then we can put 0.055 for m over t. C is 3,900. And the change in temperature is 84 minus 11. Put these into your calculator and you will get 15658.5 watts. As the number we have used above, they are too significant, then we will run it as 16 kilowatts. Part B, our previous calculation, probably it is a underestimation to the actual power input. The reason is, in practice, there should be some energy transfer as thermal energy losing to the surroundings. Next, part C, we're going to describe in terms of molecules of those liquid when it was increased from 11 degrees Celsius to 84 degrees Celsius. The answer is, firstly, because of the temperature is increased, therefore the average kinetic energy of molecules is also increased. Don't miss any single phrase. Average Ke of molecules. You need 3 important phrases. Next, because of the average speed of the molecules is higher, there will be more frequent collisions between the molecules. Part D, we have a cross-sectional view of the pipe which is containing the milk. Most of the pipe is insulated, except there is a small section of the insulation being removed. The part 1 question is, how is the energy transfer from the inside of the metal pipe to the outside of the metal pipe? Because the milk and the pipe, they are in contact. Therefore, the energy transfer here is going through as a conduction process. Part 2, you are going to calculate the energy lost in every second, which means the power. How do we calculate the power radiated by the pipe? We will take a look at the Stefan-Boltzmann law, which is P equals to emissivity, the Boltzmann constant, surface area, and absolute temperature to the power of 4. The power is the unknown, meaning the rest should be a known. Emissivity and Stefan-Boltzmann law, just leave it here. And surface area here is the surface area of a cylinder, which is the circumference times the length, or maybe times the height, depending on how you view the object here, and t to the power of 4 at the end. The emissivity is 0.40. The Stefan-Boltzmann law, you can check it using your data booklets. 2 times pi times r. R is given as 0.067. L is the length of the pipe which is exposed, therefore 0.56. And temperature must be in Kelvin. It is 273 plus 84, and then to the power of 4. And you shall get 87 watts. When you compare 87 watts to the previous answer, 16 kilowatts, you can see that 87 is very, very insignificant. What else other than conduction and radiation could be transferring thermal energy as well? Which is convection. Convection is a process of those warm milk and warm pipe would heat up the surrounding air particles. When they heat up, they will expand, getting less dense. When they get less dense, they would go up and leave the pipe surface. So the answer is convection is probably the other significant loss. Because of the reduction in density of air particles close to the pipe surface, hot air particles, they will rise, and they're replaced by those cooler air particles from somewhere else. Question 3. There are 2 loudspeakers, namely A and B. They are at the same distance from the microphone M. Imagine the loudspeaker A and B, they are connected to the same mobile phone, such that when they play music, the signal coming out from A and B, they are identical, known as they are emitted in phase. Now, the loudspeaker B is shifting away gradually, and the intensity at M is being detected a variation going between a maximum value and a minimum value you can see on the graph. You are going to give an explanation why there is a maximum intensity and minimum intensity variation. The answer is, when B is shifting away, there is a path difference between BM and AM. And such interference coming from wave A and B, they would take place at M. Because of the interference could be constructive as well as destructive, the intensity at M could be high and low. It will be a maximum intensity when they are arriving at 0° phase difference, also known as in phase. The path difference at that moment will be an integral multiple of their wavelength, n times lambda. On the other side, if it is a minimum intensity, which means they are arriving at 180° phase difference, which is pi out of phase, also known as antiphase. Such path difference will be half integral multiple of wavelength. Next, we are going to deduce the wavelength of the wave using the given information. You can see that at these points that I circle, they are going to have a in phase relationship, as well as they are creating a constructive interference. To do so, at this position, their path difference must be 0 lambda, 1 lambda, 2 lambda, and so on. And they are namely 0 lambda here, 1 lambda here, and 2 lambda here. Then you can deduce 1 lambda is about 26 cm. Or you can do 2 lambda is roughly 52 cm, which gives you 26 cm being the wavelength. And how do we give the explanation in words? You may simply start with the answer wavelength is 26 centimeter. And because this is the distance between peak to peak on the graph, and which is exactly one wavelength, so that it's giving a constructive interference. Next, part B. We're going to put a microphone at the position B, therefore here. And it was originally a minimum. Now we're going to vary the frequency such that it will become a maximum. And this is at the position of 13 cm. If it is becoming the first maximum, which means the new wavelength is going to be 13 cm, such that the same position will be a maximum. To do so, we can take a look at the V equals to F lambda equation. 340 equals to the unknown frequency times 0.13. This is the new wavelength such as to make it a maximum. The answer is 2600 Hertz, which is very close to the target, 3000 Hertz. Next, part D, loudspeaker A is now switched off, which means the only source is loudspeaker B, and the loudspeaker B is moving away at a certain speed, and it was emitting 3000 Hertz. Let's deduce the difference between detected frequency and the original emitted frequency. This is a question about Doppler effect. Let's start with the equation. F prime equals to F V plus US. US stands for the speed of the source. V is the speed of the wave. F prime is the target here. Leave it unknown. F is the emitted frequency, which was 3000. Speed of wave is 340. And the speed of the source, it was 1.5. Just put these into your calculator, then you will get 2987 Hertz. To show the difference between their frequency, we should give a subtraction between the detected frequency and the original emitted frequency. This subtraction is very straightforward. Just put them into your calculator, then you will show that it is 13 Hertz. Next, question 4. It is going to be a very complicated question. And no worries, I'm going to show you a very important and easy technique to solve all complicated circuits. In these circuits, you are given with 4 fixed resistors, with 1 variable resistor, and there is an ideal power supply, which means there is no internal resistance. Your target is to get the potential difference across P, And if you check the mark scheme, there are some more straightforward method to get through this question. But personally, I don't recommend that one because that technique is based on an assumption of two resistors or two components that are in series. What if there are three components? What if there are some more variable components? Then that technique will no longer be useful. But instead, the following technique I'm going to show you is a universal technique. You can use it on a network of 20 components and it will still work. The way to do it is grab some color pen. Let's start with the cell. On the left hand side, we make it in green. And you can keep painting green until you meet a component. Here, you meet a junction. Junction is not a component, so keep on moving. Everything here, they are green until it hits P and Q. But don't make the P and Q green. Leave it like this. On the other side, let's make it orange. As long as you are moving along wires, you can still use the same color. And then it will be orange over here. When should we change the color? When there is a non-zero current passing through a component with non-zero resistance. In other words, if there is a potential difference going up or going down, then you should change the color. Like here, the wire between P and R, it has passed through the components P and components R, in which you can find a non-zero current passing through a 40 ohm and 60 ohm. So this is another color, a third color. So as the last one, the region between Q and S, there is a certain potential difference when it passes through Q and when it passes through S. It makes it another color, violet. Why do we make so many colors? Because these color lines is going to emphasize the potential difference of different components. Let's begin with the easiest one, the cell. The cell is sandwiched by green and orange, and it is given at 6.0 volt. Which means anything between green and orange is 6.0 volts, which includes, of course, the cell, as well as those regions above. The P and R series, the total voltage is 6 volts. Then, it makes the math much easier now. Let's focus on the P and R series. Because their resistance is 40 ohm and 60 ohm respectively, then we can take an equation of resistance R equals to V over I. We take the combined PR calculation. Always make subscripts. The combined resistance is 40 plus 60. The total voltage is 6. The unknown current running through PR is therefore 0.06 ampere. These currents would then pass through the component P. So we can take a look at the resistance definition applying on P itself. It is 40 equals to unknown potential difference divided by 0.06, and your unknown potential difference is 2.4 volts. I know this technique is taking a certain time, but it works because it can guarantee you can solve all complicated network of circuits. So let's get your hand on this one. From time to time, you will speed up, and almost, maybe after a few months, you can solve everything in your mind instantly. In part B, here you will see my coloring technique is going to shine because of the color you have used. It's going to make this question very simple. First, the voltmeter reading reads 0, which means the electric potential of blue and violet, they are the same. If blue is 2 volt, violet is 2 volt. But how do we get the actual potential at different colors? Let's start with the cell. The cell is a 6 volt ideal power supply, that it should be 0 on the right hand side and 6 on the left hand side. As you travel along the wire, there is no change in potential difference. Just keep it at 6 on the green and 0 on the orange. According to part A, we have deduced the potential difference across P is 2.4, which means from green going across P to blue, it should drop by 2.4. Then it is 3.6 here. And according to the voltmeter reading 0, the violet is 3.6 volt as well. We can note that the difference between green and blue is 2.4 volts. And the difference between green and violet is also 2.4 volts. Let's take a look at the definition of resistance acting on component Q. Then the resistance is 16 ohm. Voltage is 2.4 because of the difference between green and violet. The current running through it is 0.15 ampere. And what do we do with this one? We can use this information on the component S. Component S is sandwiched by violet and orange. What is the potential difference of S? The difference between violet and orange is 3.6 volts. So let's take a look at the new equation here. We have S being the subscript. RS, it is unknown. V subscript S, it is 3.6 according to the violet and orange we had above. Current is what we have on the left hand side as they are in series, 0.15. Therefore, the resistance of S, it is 24 ohm. And this is the answer of part B. Part C1. The previous object, it is now being extended into 4 times of its original length. So this one could be the original length and cross-sectional area. Then the new one is much longer, but it came from the original object, which means they should share the same volume. If it is much longer, then it should be much thinner as well. It should be 4 times the length in the expense of a quarter cross-sectional area. The resistance of a conductor should go as this equation: resistivity times the length divided by the cross-sectional area. The material is unchanged, so you can conclude the resistance is directly proportional to L and inversely proportional to A. Given the factors of 4 times length and a quarter cross-sectional area, the new resistance is 16 times of the old one. And it is 16 times 24, therefore it is 384 ohm. Because of the component S is reshaped, the power dissipation in component Q is going to change as well. As Q and S they are in series, one change on the S might influence the behavior of Q. Let's take a look at the P equals I square R equation applying on component Q. The resistance of Q itself is unchanged because it is a fixed resistor, but the current going through it is going to drop because the whole QS series, the total resistance is going up and therefore the current is reduced. To balance the right hand side and left hand side, the power dissipated at Q should reduce as well. And you may give your answer as to follow. The power dissipated at Q is reduced because of the current in this branch is reduced and following the result of P equals I square R. Question 5 is about particle physics. Here we are going to describe the structure of a baryon. Firstly, there are 3 quarks for sure. And also there are some more information about its structure and properties. For instance, you can describe its electric charge, you can describe its baryon number, stuff like this. And the following are some examples of accepted answer. The electric charge must be an integer. It could be +1, -1, or 0. The baryon number is +1. If you are describing an anti-baryon, then the baryon number, however, will be -1. And all the quarks in a baryon, they are held together by strong force, nuclear strong force. In part B, you are given with a Feynman diagram. In this diagram, there are few different decays happening. Let's start with decay A. At decay A, you can see the exchange particle is a W plus boson, and it is a clear evidence it's gonna be a weak nuclear interaction. How about interaction B? At interaction B, there is a gluon, and it makes it a strong nuclear interaction. In part C, you can see a decay equation, and you're going to deduce is it a strong, weak electromagnetic or gravitational interaction. It's not complicated because you can judge it by telling its strangeness. The strangeness on the left-hand side is non-zero because you can see there is an anti-strange quark. Therefore, the strangeness on the left-hand side, it is +1 going to 0 and 0, as the muon plus and the neutrino, they are lepton, they are not quarks. Therefore, the conclusion is this must be a weak interaction because the strangeness is not conserved, and this is only possible when there is a weak interaction. Question 6. There is a mass spring system and it is oscillating on a frictionless staple. The acceleration of the mass is varying with its displacement from the equilibrium as shown in the graph. And using this graph, we can tell it is executing a simple harmonic motion only when the acceleration is small and when the displacement is small. The reasons are the displacement is directly proportional to the acceleration, clearly because of it's a straight line going through the origin. And also the displacement and acceleration, they are always in opposite direction, because of the gradient is negative. Part B, we're going to calculate the time period of the system. The time period of the system is going as 2 pi over omega, and meanwhile omega is going as this equation, negative omega square x. You can find this equation in your formula sheets. And using the second equation here, clearly it's about the gradient of the straight line, just mimicking y equals mx. Therefore, the m is the gradient. The negative omega square is the gradient. Let's start with deducing the gradient of the graph. Maybe we can take this point and this point respectively. Their coordinates are negative 0.1 and 2.8. On the right hand side is positive 0.1 and negative 2.8. Let's put these together to get its gradient. It is 2.8 minus negative 2.8, and then it's negative 0.1 minus 0.1. So the gradient is negative 28, and there is a unit. The unit is as negative 2. The negative omega square is negative 28, therefore omega is 5.3 as negative 1. Lastly, you can get the time period by 2 pi divided by omega. So it is 2 pi divided by 5.3. The time period is therefore 1.2 seconds. In part C, we're going to deduce the change in time period when the displacement is getting larger and larger. The gradient is going to reduce. The gradient is negative omega square. It's reducing, and therefore omega is reducing as well. By the equation of time period equals to 2 pi over omega, the time period, however, is getting larger. Part D, we're going to build a new graph, but they're still referring to model A and model B. The given graph is about model A, and next we are going to draw the corresponding graph of model B. And let's refer the graph on the left first. When the displacement is within 0.04 meter, basically these two graphs, they're identical. So on the right hand side, basically we can assume when the displacement is 0.05 in the negative side and the positive side, they are practically the same. But next, which is when the displacement is going beyond 0.04, then the graph, they are not the same. The omega for model B is getting smaller. Therefore, according to the equation of E equals to half m omega square x0 square, with a lower omega, there should be a lower energy. Then the graph would be always underneath the black line because there is always smaller and less energy. And how long should this line extend? According to the graph on the left hand side, both graphs, their amplitude, no matter A or B, is 0.10 meter. And we should obey this rule on the new graph as well. Don't let the line extend 0.1 on the positive nor the negative end. And this is your graph. According to the question command term, we should describe the graph for model B in words. It would be the same curve for small amplitudes up to about 0.05 meter. And for those displacement beyond 0.05, the EP, the potential energy, will be smaller for model B. Question 7. There are two identical point charges, X and Y. Between X and Y, the midpoint is known as O. The electric potential at O is a result of the X and Y. So V of O is because of the X and the Y acting at O. The value of their electric potential follow this equation. You can find this in your formula sheet. Make sure you are giving the subscript X acting on O, X acting on O. So as the other one, Y at O and Y at O. So you have the charge of X, which is 4.0 times 10 to the power of negative 6. The distance is the midpoint between their separation, 0.15. The other one is completely the same, so I skip it here. Just put them into your calculator, then you will find 4.8 times 10 to the power of 5 volts. Part B, we're going to plot a graph. The graph is V against distance. It should be an exponential decay graph if you map it with the spherical object down here. Then you have two objects, X on the left and Y on the right. Therefore, their graph should look like this one. X going to here and Y going to here. When you put them together, the resultant graph should be going as follows, like a well. And it is not touching X. If you put a dotted line here, you can see that it's not touching X nor Y. In part C, there is a positive charge at Z, and this object is repelled from X and repelled from Y as well, because literally every particle here, they're all positive. When it is locating on the left hand side of O, the repelling force from X will be very strong. But when it is locating on the right hand side, the repelling force from Y will be dominating. Therefore, the force is always points at O. Is such oscillation an SHM? The answer is no, because right now the force is proportional to 1 over r squared. What's being required is F being proportional to X. So we are not having an SHM now. Question 8. There are two capacitors, C1 and C2, connected in parallel with your power supply. We are going to show the charge stored on C1 is going to be about 0.04 millicoulomb. And because it is a show that about question, make sure your answer is at least 2 sig Fig. Let's start with the capacitance is the charge over the potential difference. And we can rearrange it to get charge is the product of capacitance and voltage. 28 microfarad times the voltage 1.5, and it is 0.042 millicoulomb. In part B, the switch is moved to position B, therefore you have the following circuits. You have a C1 on the left and then C2 on the right. The C1 on the left, it is 28 microfarad. The voltage is 1.5 volt and the charge is stored is 0.04 millicoulomb. On the right hand side is capacitance is 22 microfarad. The voltage is 0 and the charge stored is 0 as well. But this won't last forever because it's forming a new circuits completed together and therefore they must strike a balance. The voltage will therefore be the same. In the end, it will reach a state of this one. It's still 28 microfarad and with a new voltage, unknown voltage, and a new charge stored, and namely V1 and Q1. On the right hand side is 22 microfarad, and also there is the same voltage as they are in parallel, but the charge stored could be different now. Firstly, identifying them, they are in parallel because they share the same PD. Next, knowing that they are in parallel, the total capacitance is the simple addition of their individual capacitance, which gives you 50 microfarad. And we shall take a look at the total capacitance as a ratio, Q of total and V of total. The total capacitance is 50 micro, but the total charge is the same as the old one, which is 0.04 times 10 to the power of -3, and Vt is the unknown here. You can deduce Vt, it is 0.8 volts. Let's compare the energy before switching to B and after switching to B. Original energy, let's put down original. It was half CV square, which is half times its capacitance, only C1, therefore 28 micro, times the voltage 1.5 square. Then you get 3.15 times 10 to the power of -5 joules. The new one, it is half the capacitance of C1 is remain at 28 micro, and the voltage of it will be 0.8 square, so the energy is 8.96 times 10 to the power of -6 joules. Take a look at the subtraction between them and you can find energy transfer. It is 2.3 times 10 to the power of -5 joules. The energy transfer to C2 is not as the energy transfer out from C1, because some energy is not only going to C2 but also dissipate to surrounding as heat. Part C, we have a coil Y looping around the coil X. The coil X is connected to a cell, however, initially it was an open circuit. When it was an open circuit, there is no current. When there is no current, there is no magnetic flux linkage at all. Once the circuit is closed, then there is a current running through X, and there will be a magnetic flux linkage in Y. There is a change in flux linkage at the instant of closing the switch. But after closing the switch, the magnetic flux linkage will be constant. A constant magnetic flux linkage is not inducing any EMF. Therefore, the answer here is there will be an initial deflection on the voltmeter. After that, it will fall back to 0. The reason is EMF is induced only while the flux is changing. Next, using the graph, we are going to determine the average induced EMF only for 3 milliseconds. The induced EMF, it is negative delta flux linkage over the time taken. If we are studying the magnitude only, then we can take the absolute value. The change in flux linkage is also known as N times B times A, and then divided by T. The N is the number of turns, which is 5 turns on the left-hand side. And the magnetic flux density, it is roughly 7.5 times 10 to the power of negative 3. The area, it is 6.4 centimeters square, which is 6.4 times 10 to the power of negative 4 meter square. The time it took is 3 times 10 to the power of negative 3. Put these into your calculator, then you will get 8.0 times 10 to the power of negative 3 volts. Question 9. A beta decay starting from potassium 40. Then it will go through a beta negative 1, an antineutrino. Lastly, it's going to be a calcium. It will be 40 at the top and 20 at the bottom. Question B. You are given with a new decay process. Potassium 40 going into argon 40. This decay is only accounts for 11% of the decay. Assuming that originally you have a bunch of potassium 40 and part of it is not going through the decay, which is 340 micromole. It will remain as potassium 40. About 12 micromole is going into argon 40, with an additional amount of particle going into calcium as described above. This is going to be 11% of the decay, which means the calcium will account for 89%. What is the total amount of particle overall? We can get the amount of particle going into calcium by the following calculation. The amount of decayed potassium 40 is 12 micromole divided by 0.11, 109 micromole. So the total potassium 40, including those did not go through any decay, should be 340 plus 109. It gives you 449, which is very close to your target 450. Next, we are going to determine the age of the rock sample. Starting with the half-life being provided, we can get the decay constant through this hidden equation. It is an hidden equation. It is not given in your formula sheet. Please remember this equation. The half-life we put, just keep it as the unit provided. Therefore, in years. It will be 5.3 times 10 to the power of negative 10 years, negative 1. Next, we compare the before and after decay amounts of particle. N equals to n sub 0, e to the power of lambda, and t. N is the current number of particle. It is 340. N sub 0, it was the original number of particle, which is the answer in part 1, 450. The lambda is the one we had above, 5.3 times 10 to the power of negative 10, and time is the answer here. Just rearrange them and you will get 5.3 times 10 to the power of 8 years. In part C, you're going to outline how the decay constant is determined in a laboratory. It is impossible to use the equation of natural log 2 over T half anymore. The reason is half-life of potassium is billion of years. We cannot carry out an experiment for billions of years. So we should abandon this idea. We use something else. This is the equation you need, but unfortunately, it is not provided in your formula sheet, so please memorize this equation as well. A is not tricky. You can get it measured using a GM counter. How about N? We can't use a magnifying glass and count the number of molecules one by one, right? And we can measure or calculate the number of particles by studying its mass. Because with a greater mass, there shall be greater number of particles. For instance, if there is 80 grams of potassium 40, then you can tell there are 2 moles of particles. 2 moles of particle is 2 times the Avogadro constant number of molecules. That's how we get the exact number of particles. To conclude, your answer should be: first, use the mass of the sample to determine the number of potassium 40 atoms. Next, use a GM counter to determine the radioactivity coming out from the source. Use the equation A equals to lambda n to determine the decay constant of your sample. This is the end of the paper. Feel free to make your request for the next complete solution. And I will see you guys next time.